As introduced, I'm Burcu Çelikol. I'm a project lead at IMEC One Planet Research Center based in the Netherlands. And I will talk a bit about air quality sensors and specifically data quality and calibration of sensors. So Pavel touched upon this topic before, but I wanted to start again with the question, why do we measure air quality in citizen science projects? So firstly, there are highly accurate traditional monitoring networks, such as those expensive sensors that Paul mentioned that are deployed around our countries, for instance, by environmental agencies. But these are quite sparsely distributed, so they may not be capturing local variations in air pollution, such as pollution hotspots in the cities. And the citizens that live in urban areas are, of course, impacted by a poor air quality, and especially those in under-resourced communities where sources of pollution tend to be closer to housing, where people are spending time. And this is exactly where citizen science can come in. So the initiatives from citizen science that we have can help point to areas of concern and perform measurements and gather evidence to drive change, whether that's awareness or behavioral change, and eventually also affect policy. But in order to start talking about policy-ready data, what we need to ensure is data quality. And it's not about having the most accurate measurement possible, but it's about having sensor data of known quality in the end. So I included a quote here, which I like: data of poor or unknown quality is less useful than no data, since it can lead to the wrong decisions. So citizen science air quality sensors tend to be, by definition, low cost, right? And these components, these simple components, can be sensitive to environmental influences. So, for instance, if you're measuring particulate matter, you have an optical sensor which is detecting airborne particulates in air, if you have high humidity conditions, for instance, there might be water molecules that absorb on your particle, and that particle will be detected as if it's larger than the dry weights, and your concentration will be overestimated in the end, so you will have a higher signal than the dry fraction. And this is the kind of things you can compensate with calibration. There's different calibration approaches you can use to help reduce these influences and improve your data quality. But one of the Menti answers was also about managing expectations. And it's also important to realize with low-cost sensing comes different kind of measurement principles, which inherently are less precise. So let's say we're measuring particulate matter concentration in air, and the true value of your PM concentration is the bullseye. And if you're making like 6 measurements using a reference sensor which is well calibrated, then the results you see would be the one that's depicted on the left side, so the number 1. So that would be the output of your reference monitor. But if your reference monitor was uncalibrated, you could see the 6 results that look like number 2. And in the case of low-cost sensors, you have low accuracy and precision, which means that your results may look like, if you buy a random sensor, your measurements could look like number 4. And what we're trying to do using calibration, by compensating for these environmental factors, is to bring 4 more towards 3. So that you have higher accuracy, but your sensor may still have low precision, and by a scale of numbers, so deploying many sensors, then you can have a reasonable impression of your local hotspot or whatever you would like to measure in your citizen science campaign. And what's important also to realize is that, let's say you do a calibration at one time point, but environmental conditions are changing, or maybe the sensor components that you're using are aging. So that means that your 3 the calibrated local sensor can still move towards 4. And for that, depending on how long your deployments will be, you may have to try different approaches in order to make sure that you stay in number 3. So now that we've set some expectations, let's talk a bit about the calibration approaches. And the first thing before going into calibration, what I want to mention is one thing to start off to be able to calibrate your sensor is to make sure that you're using citizen science sensors in your project in the first place that have been somehow used and benchmarked before. There's a lot of studies, for instance, by research institutes, environmental agencies, where this benchmarking, which means deploying your local sensor that would measure your pollutant of interest outdoors next to a high-end reference equipment, acquiring data for a certain amount of time, and quantifying basically the results of and checking that next to the reference results. And if you do a pre-study before starting your citizen science campaign and use sensors that have been benchmarked before and have gotten good quality labels, then you're starting off at a good level, and calibration can only help more. Okay, back to calibration. There's 2 questions in terms of calibration. One of them is how do we acquire the calibration data sets? And the second one is how do we calibrate? So in order to acquire the calibration data sets, so that's like having your local sensor measurement and reference measurement next to it so that you can train your model. There's a few approaches. One of them is laboratory calibration. So that's taking your local sensor using a laboratory facility if you have access to it and exposing the sensor to certain amounts of pollutants. And with these steps, making your calibration curve and using those parameters that you extract from that curve in order to apply them during your deployments. The next one is field calibration. So that's basically what the benchmarking is as well, that you deploy your sensors next to a higher grade reference station during a certain amount of time. This is usually from weeks to months. And this tends to perform better because basically the sensor is in the same type of environmental condition that it will be eventually deployed in. So then as long as you're acquiring data that is similar to the deployment conditions, then the calibration is more likely to stay valid. And there's also novel approaches, such as nighttime calibration, where the idea behind it is that there's most of the air pollutants are produced from human activities. During the nighttime, when there's a lot less human activities taking place, then basically you can use the reference stations around your local sensor and determine a certain diameter and basically baseline your sensors to the reference sensors during the nighttime in order to use the calibration parameters that you extracted during the daytime. The second question is, how do we calibrate? So that's your model. And this could be, I'm not going to go into different models for the sake of time, but it could be a very simple linear regression model that you base your calibration on. Basically, you acquire raw sensor data and data from adjacent sensors, such as a temperature humidity sensor, which also exists in many of the citizen science sensor systems. And you use the reference station data or your lab data as the ground truth, and you build your model depending on this. And it could look like the equation that I'm showing there, that you have only 3 parameters for calibration. And there's more information about this kind of approach in the links that are underneath the slide. So how do we evaluate calibrated sensor data? So there's a few metrics that you can calculate that's to look at also how well your raw sensor measurements are performing and how also your calibrated sensor measurements perform compared to the reference data that you have. So some of these metrics are Pearson correlation coefficient, mean absolute error, expanded uncertainty at limit value, and all of these, the definition for all of these you can find in the link below. But basically it tells you how well you match with your golden truth data. And then, for instance, correlation coefficient is one of those metrics which says, okay, if you have, if it equals 1, then you have a perfect match between the local sensor data and your reference sensor data, and you calculate this for raw calibrated data. And if for your raw data, it's 0.4 and it has increased to 0.6 with calibrated data, then you know that there's a benefit to your calibration model. And there's also European protocols that you can use to evaluate the sensors, which the new versions of these are also includes classification of sensors. So one for gaseous pollutants here, this 176601 has been published, and one for particulate matter is being prepared right now. And these are guidelines you can use in order to classify the resulting sensor data using these metrics. So for instance, then that will tell you that your PM measurements has an uncertainty between, if it has an uncertainty between 75% and 200%, then it's only an indicative measurement and it can be used as that, and that is not a quantitative measurement. But at least then it is, you know, the quality of the data that you're using. So knowing all of this, how did we approach calibration and compare? So Lieven will talk a little bit more about what kind of sensors we have in compare, but basically what I want to say here is that we have been measuring using 4 different sensor types, 3 different parameters. We had SODAC air sensors, which measure particulate matter, which are mobile sensors, and sensor.community sensors, which are static PM sensors. We had also One Planet NO2 sensor prototype, which measuring nitrogen dioxide, and BC meter prototype measuring black carbon. And all of these sensors were benchmarked during the project so that we had a reasonable understanding that the sensors were performing sufficiently for the experiments that we wanted to make. And in order to be able to calibrate all this sensor data, we also used a data standardization, because that allowed us to be able to use the same kind of pipeline for online data calibration. Different kinds of sensors usually have different data models. And we use Open Geospatial Consortium Sensor Things API model in order to transform the sensor data so that we can calibrate these different, like particulate matter and NO2 sensors using the same kind of pipeline without having to change and make a new model for each type of sensor. And we use a hybrid approach in compare for calibration. So so I mentioned nighttime calibration before. We use something similar, but our sensors were stored indoors during the nighttime. So we changed it to low variance type of calibration. And there's more information that you can see in the deliverables, also in the link that I shown here below. And we implemented the calibration approach as a near real-time cloud-based calibration. So basically the raw data was ingested and in the cloud, there was a model, calibration model running, which was a multilinear calibration. And basically there was a moving window where a certain amount of data was calibrated in near real time and made available to the dashboards in compare. And this is a sneak preview also of the results. On your right side, you see a plot, and on the x-axis is particulate matter, a local sensor data, so that's concentration in micrograms per meter cube. And on the y-axis is the reference sensor data. And blue is raw and orange is calibrated data. So here you can see that the raw data was quite overestimating. The response was quite overestimated compared to the reference, and this overestimation was corrected using the calibration as a service. So a few take-home messages. Less data of known quality is better than more data of unknown quality, because you can actually use it to analyze your experiments. And researching before selecting your citizen science sensor is quite important. And if you have sensor that doesn't have a known quality of data, then basically you can do all sorts of calibration methods, but it could be that you're just not measuring your pollutant of interest. There's many calibration approaches, such as the ones I mentioned during the presentation, so you can tailor depending on resources, for instance, whether you have access to these reference stations or not. And you can also tailor depending on your desired outcome. How much do you want, how much uncertainty of your measurement is acceptable to you? And the last point is, knowledge sharing is important. Reaching out to those who have experience dealing with data in citizen science projects usually brings the best results, so that you can also learn from their experiences and build on each other's knowledge, so that your participants can contribute meaningfully to your citizen science project. And that's kind of it from me.